All right. Looks like we're still missing a couple people, but we'll go ahead and get started then on the first problem. So for the first problem, we have a problem on sequences. So here we have this recursive sequence. So we've got ak equal to 2ak minus 1 minus 3 for all k greater than or equal to 2, where we have this initial condition that a1 is equal to 4. And then we have this guess for this closed form formula for r sub n. And we guess the closed formula is a sub n is equal to 2 to the n minus 1 plus 3. And then what we're asked to prove first is to show, does this predicate r1, representing the closed formula, does that give the same values that the recursive formula does? So if you want to go ahead and just take about a minute to go through those and check that the closed and recursive formulas give the same values for 1, 2, 3, and 4. So we can just go ahead and check that. So let's go ahead and we'll do the recursive on this side. So we're given a1 is equal to 4, a2, well, using the recursive formula, that's 2a1 minus 3, which is 5. And then a3, that's just 2 times a2 minus 3, which is 7. A4 is 2 times a3 minus 3, which is 11. And then if we use the closed formula, for r1, just using the closed formula, we've got a1 equal to 2 to the 1 minus 1 plus 3, which is 5. a2 is 2 to the 2 minus 1 plus 3, which is 7. Or excuse me, that's, whoops. Yeah, so that's 4, because 2 to the 0 is 1, so 1 plus 3 is 4. 2 to the 1 plus 3 is 5. a3 equals 2 to the 3 minus 1 plus 3. 4 plus 3, 7. And a4 is equal to 2 to the 4 minus 1 plus 3. And that's 11. So not too bad. We just verify that all of these hold for R1, R2, R3, and R4. So this wouldn't be a proof to show that these are actually equivalent. We'll do that in the next problem, but this just shows us that, hey, for the first 4 values, the recursive and closed formula give the same values. So next, we're asked to write R8 and R9. So let's get another page here. So R8 and R9. So let's just go ahead and write those out directly. So R8, we just use the closed form formula. So for R8, we're given that A8 is equal to 2 to the 8 minus 1 plus 3. And so we've got 2 to the 7 plus 3, and that's just be 131. And then for R9, we have A9 is equal to 2 to the 9 minus 1 plus 3. So we've got 2 to the 8 plus 3, so that'll be 259. So we're done with that part. Just using closed form formulas here to write what R8 and R9 are. And then now in part C, we're asked, hey, that we've already verified that R8 is correct. So we've already shown that the recursive formula agrees with what R8 says. And we need to show how we could verify R9 without starting from the beginning and verifying R1, R2, et cetera, et cetera. So anyone have any idea for how we could show that R9 is correct?
You can use the recursive formula and you can just use the value from R8 since that's the only variable that you'd need to plug into the recursive formula.
Yeah, perfect. So for the recursive formula, yeah, we've got a sub 9 is 2a8 minus 3. We already know that the value R8 is correct, so we know that the value for A8 is correct. So we can go ahead and use this formula. So that's 2 times 2 to the 8 minus 1 plus 3 minus 3. And then we multiply out, so we get 2 to the 8 plus 6 minus 3, or 2 to the 8 plus 3. And if we did this again, we would get 259. And what I want you to notice here is, so here we started with the recursive formula, which we know to be true. And what did we end up here? Well, we ended up with this is actually just the closed formula, 2 to the 8 plus 3, and the value holds. So this is how we can verify that R9 is correct. So any questions on this part, on parts A, B, or C of this problem? No? Awesome. Yeah, it's a pretty straightforward problem here. But for the next part, what we're actually going to do is we're going to take that same recursive formula we had, and we're going to prove that, in fact, it is the same as the closed formula. And then we have a hint in this problem, so we want to use induction in order to go through this proof. So remember that with induction, we have the 4 parts to every induction proof. So first we have the problem statement. So somebody want to give, what would we have as a problem statement here, or what would we say that P sub n is in this problem? So either type in chat, raise your hand. Yeah, so the first equation is equivalent to the second we have in chat. And yeah, so what we can do is we can basically say, hey, P sub n just represents that the recursive formula is equivalent to the closed form. And then what we could do here is we could say that, well, A sub n is 2, a n minus 1 minus 3, a1 equal to 4 is equivalent to a sub n equals 2 to the n minus 1 plus 3. So the crucial thing here to note is we're not using the same variable k anymore when we're introducing this recursive formula here. And the reason why is because P of n, when we have the problem statement only knows about what n is. So we need to have all of our variables in terms of n. But yeah, this is what we could have for the problem statement. And then for the next part of any induction proof, we have to do the base case. Or we have to prove that the problem statement is true for the first value. In this case, it'll be 1. So we have from the recursive formula that a1 is equal to 4. And then if we use the closed formula, we have a1 is equal to 2 to the 1 minus 1 plus 3, which is 1 plus 3, which is 4. So that's the base case holds. The value from our recursive formula is same as the value from the closed formula. And then the third part of any induction problem is we have the inductive hypothesis. So someone would want to say either in chat or just by raising your hand, what would be the inductive hypothesis? Or what could we use as the inductive hypothesis for this problem?
To assume that P of n is true, and
Yeah.
then checking for P of n plus 1.
Yeah, so the inductive hypothesis there is that P sub n is true. And then the inductive step, yeah, will show exactly what you're saying. We'll prove that P sub n plus, that P of n plus 1 is true. So inductive hypothesis, we're going to say that P sub n is true. Or in other words, whenever we see A sub n is equal to 2an minus 1 minus 3, we can go ahead and replace it with an equal to 2 to the n minus 1 plus 3. And this will be the important substitution component that we're going to use later from our inductive hypothesis. Because whenever we're doing induction, there's always going to be some point we're going to use the inductive hypothesis to substitute what we've assumed to be what we assume it to be equivalent to. So any questions on the first three parts of induction here? Awesome. So let's go ahead to the final part of any induction problem. So when we'd use the inductive step. And so here, because we assumed that P of n is true, we need to show that P of n implies P of n plus 1. Note that we could have also said, for our induction hypothesis, we could have assumed that P of n minus 1 is true. And then in the inductive step, we could have shown that P of n is true. Both would work fine. So if we need to show that P of n implies P of n plus 1, then we need to find what the value is for A of n minus n plus 1. So using the recursive formula that we had for A of n plus 1, we know that A of n plus 1 is 2 an minus 3. And then here's where that induction hypothesis is going to become handy, because we already know what A of n is. We've assumed that P of n is true, so we know that the closed formula that we have for A of n is true. So we can go ahead and substitute A sub n with what the closed formula is, or 2n minus 1 plus 3. And then this is by our induction hypothesis. And then we can just simplify the algebra. So we've got 2 to the n plus 6 minus 3, which is 2 to the n plus 3. And this is exactly what we wanted to prove here. We wanted to prove, if we remember, if we go back to the problem statement, we wanted to prove that the closed formula A sub n is equal to 2 to the n minus 1 plus 3 is true. And that's exactly what we have for here, but with n plus 1. So thus, P of n implies P of n plus 1 so thus our statement holds for all n greater than or equal to 1. Any questions on this problem on induction? Awesome. So let's go ahead and move into this problem on the pigeonhole principle. So this is what we covered this week in lectures. So here we're asked to use the pigeonhole principle to prove the following. So we're given any 5 integers, and we want to prove that there's going to be at least 2 of those integers that have a sum or difference divisible by 7. Right? So I want you to just go ahead and take a minute to kind of think about this problem and think about some of the formulas that we're going to use from the pigeonhole principle to figure out how many containers we're going to need for this problem. So just go ahead and take a minute to kind of think about this problem and how we're going to go ahead and start it. All right, so hopefully you've had a chance to think a little bit about how we might start this problem. So the first thing to note, whenever we're using the pigeonhole principle, we're always on the lookout for how we can solve for those variables m and n that we introduced in that pigeonhole theorem. So note, the important numbers to take out of this is we have any 5 integers. So this is the total number of items we have is 5. So what's the formula? Someone wants to type in chat or raise their hand. What formula are we going to use to express that 5 is our total number of objects that we have? So remember, this will be the formula that uses m and n. Yes. So perfect. We have it in chat. So yeah. So the formula is m times n plus 1 is equal to 5, where 5 represents the total number of items. And then the other value to pay attention to in this problem is that we have 2 items that are going to have a sum or difference divisible by 7. So we're saying that at least 2 objects are going to have this property. So what formula will we use from the pigeonhole principle to express this? That we're going to have at least 2 objects that have this property, or we're going to have at least 2 objects that fit in one of these boxes. Yeah, perfect. So somebody said n plus 1 equals 2. Yes. So n plus 1 is equal to 2. And this where 2 represents the value that we have at least this many objects. In a box. And then now we've got 2 equations. We've got 2 unknowns for m and n, so we can go ahead and solve for these values. So we can go ahead and solve for n. So using n plus 1 equals 2, then we know that m is equal to 1. And then when we solve for n in the top equation, we've got n plus 1 equals 5. So n is equal to 4. So can anybody tell me in chat, what's so important about this variable here? Or what does n equal to 4 mean? Yeah, perfect. So somebody said in chat, that's the total number of containers. Yes. So n represents the total number of boxes. So the important thing to remember whenever you have a pigeonhole problem is you're usually going to be given 2 of these variables. You're either going to be given so these are kind of the 3 equations that we use, m times n plus 1, or n is equal to 4. And usually in the problem, you're going to be given 2 out of these 3, and you're going to need to solve for the other one. So for this problem, we know we're going to need 4 boxes. And then what we want to think about here is with these 4 boxes, how could we put items in these boxes? They're going to be really helpful for this problem. In other words, that we're going to be able to show that any 2 of them, or that at least 2 items, when 2 items are in a box, then they have a sum or difference divisible by 7. So go ahead and take just a minute to think about how we're going to label these boxes so that we can go ahead and prove this problem. So does anybody have any ideas, just either in chat or raising your hand, for how we could kind of sort or put items in these boxes? So it looks like we've got one in chat. So we could sort by the ones digit being 0, 7, 1, 6, 2, 5, 3, 4. That's a good idea. And you're on the right track there. But yes, so somebody put in chat, yeah, what about 8 and 9? So you are on the right track with 0, with sorting the values that way. So is there something we could do then to guarantee that a number, that we're going to be able to put it into a box that has 0, 1, 2, 3, 4, 5, 6, or 7? Maybe rather than looking at the ones digit, what's something else we could look at? Yeah, so we've got, two comments there. We're basically going to be looking at the remainders. So for box 1, we're going to think about all the items in here having remainder equal to 0. For box 2, remainder is equal to 1, or the remainder is equal to 6. 3, remainder equal to 2, or remainder equal to 5. And 4, remainder equal to 3, remainder equal to 4. And so these are going to be how we sort our objects into these boxes. And why did we pick this? Why did we pick to look at the remainder here? Well, what we want to be able to do is, since we're looking at the sum or difference of integers divisible by 7, what we notice here is that the sum of both of the remainders 1 and 6 is 7. The sum of the remainders 2 and 5 is 7. The sum of the remainders 3 and 4 is 7. So that means if we have 2 integers that have remainder 1 or remainder 6, et cetera, we're going to be able to prove that those are going to be divisible by 7. And so that's kind of the key there that led us to pick these as what we're going to put into our boxes. Now, don't get discouraged if you didn't quite see that. Pigeon principal problems pretty much come down to this question, which is how am I going to label my boxes in order to prove the statement? And so it just takes some time. So, if it was a little bit of a struggle to kind of see this as an idea, go ahead and do some more practice problems, or stop by our help hours or office hours to get a little bit more help with some of these Pigeonhole principal problems. So then we can go ahead and continue with the rest of the proof. So if we're asked to prove that that there's going to be 2 that are going to have a sum or difference divisible by 7, the first thing we should do is we should say, hey, I know that that one of these boxes is going to have at least 2 items. So first we can kind of say that we're going to create 4 boxes. And place items in boxes just based on the remainder. Whoops. I'm going to divide by 7. And then we know that by the Pigeon principle, one of these two boxes, or at least, I guess one of these boxes, one of these boxes, will have at least 2 items. And so then, now that we've kind of set up the problem statement this way, we've created our boxes, and we know that we're going to have at least 2 items in the box. Then now we have to prove that in any case, if 2 items are in box 1, box 2, box 3, or box 4, that we can prove that any 2 of those values that are in there have a sum or difference divisible by 7. So let's go ahead then, and we can start. I guess, does anybody have any questions on the setup for this problem that we have here before we start going through the cases? No? Awesome. So let's go ahead with kind of our case 1, where we have 2 items in box 0. So what does that mean if we have 2 items in box 0? Well, that means, or I guess in box 1, that means that their remainders, both of the remainders, are equal to 0 when we divide by 7. So let's try to express that a little bit more formally. So let's let 2 integers k1, k2 that are integers be in box 1. Then by definition, k1 is equal to 7 c1 plus 0. So we can just say that it's equal to 7 c1. And then k2 is equal to 7 c2 with c1 comma c2 being integers. So does anyone just want to quickly type in chat, how do we know that that's the case for these 2 integers, that we can write them in this form? Yeah, division theorem. So if we have 2 values that look like this, then we can go ahead and let's take a look at the sum. So then we have that k1 plus k2 is 7c1 plus 7c2, which is 7c1 plus c2. And since it's 7 times a number, then by the division theorem again, k1 plus k2 is divisible by 7. And then by division theorem. So this is our first case where both of our items had to have remainder 0. So now we want to kind of think about the other possible cases when they either both have remainder, when they either have remainder 1 and 6, or 2 and 5, or 3 and 4. And one thing I want to do here, because somebody asked about it in the last discussion session, is there a way that we can prove for boxes 2, 3, and 4? Is there a way we can prove the statement is true for boxes 2, 3, and 4 in one step, rather than proving each box as a separate case? And there is. And so we're going to go over a little trick that allows to make some of our Pigeon principle proofs a bit easier, where you don't have to cover all the cases. You can cover all the cases kind of together if you make some assumptions. So let's make our next case. We're given 2 items, both in either box 2, 3, or 4. So is there something we know about if we're given any two items in one of these boxes? Is there something we know about the remainders here? So can somebody tell me if we're given, say, two items, yeah, perfect. So somebody said, yeah, so either the remainders are the same. So if I pick two items out of any of these boxes, either I've happened to pick two that are R1, or I've picked two that have remainder 6, or in any case, if they have different remainders, the sum of those remainders is 7. So we can talk for this proof in general about these boxes. So let's do the first case. So we kind of have a subcase here. Both integers have the same remainder. When divided by 7. So then the two integers we've got, k1, k2 are integers. So k1 is equal to 7c1 plus r. And k2 is equal to 7c2 plus r. Or c1, c2 are integers. And 0 less than or equal to r less than 7. So why here did I let r and r be the same variable? Often in our proofs, we don't want to do that. So why in this case did I let both of these have the same variable r for the remainder? Someone wants to type in chat. Yeah, so in this case, we can kind of think about it like that, as it is any number between 0 and 7. So we're being general. It could be any of the values in boxes 1 or boxes 2, 3, 4. But yeah, so like Parker's saying, because in this case, I said both integers have the same remainder. So we can let r be the same value here. So now the trick is we've looked at both of these two values, and then remember, we're still proving that we either want the sum or the difference to be divisible by 7. And so here we can actually show that the difference is going to be divisible by 7. So if we take k1 minus k2, that'll be 7c1 plus r minus 7c2 plus r. If you notice here, the r's are going to cancel, and we'll get 7c1 minus 7c2, or 7 times c1 minus c2. And this is divisible by 7 from the division theorem. So in any case, no matter which two items we picked in box 2, 3, or 4, if they had the same remainder when divided by 7, then the difference can be divisible by 7. So yeah, so somebody asked, why do the first case with 0 if it also fits this case? Yeah, that's a really good question. That's a fabulous question. Like, hey, couldn't we have stuck case 1 down in here? And the answer is no. And that's where we're actually going to get to the second subcase. That is unique to boxes 2, 3, 4. So remember, if we look at box 2, 3, and 4, what's unique about these boxes is that there's two possible remainders in each box. R equals 1, R equals 6, R equals 2, 5, 3, and 4. But box 1 just had one remainder in it. And so that's why when we're talking about here, we would have to have kind of done a lot of exclusion to say, well, if we're in box 0, then this next subcase doesn't count. So it's just easier. It makes it a little bit more clear to do just the separate case for box 1, and then talk about box 2, 3, and 4. But yeah, really good question. So now we can get on to the final subcase here, like we were talking about earlier. So we could have either picked two items that had the same remainder in that box, or they have different remainders. So then we've got K1 is equal to 7C1 plus R1, and K2 is equal to 7C2 plus R2, where again, we've still got C1, C2 are integers, but here we have where R1 plus R2 is 7. And that's like we were talking about before with the boxes. No matter if we're in box 2, 3, or 4, if they have different remainders, the sum of those remainders is equal to 7. Then here we can look at the sum of the values because we want R1 plus R2 equal to 7. So if we look at the sum of K1 plus K2, then we get 7C1 plus R1 plus 7C2 plus R2. That'll be 7C1 plus C2. Remember, R1 plus R2 is equal to 7. So that'll be plus 1. And this is divisible by 7. From the division theorem. So now we've covered all the possible cases. We're either in box 1, where they both have the same remainder, and so summing them was divisible by 7, or we're in boxes 2, 3, and 4, and then there were two subcases. Either both the integers had the same remainder, or they had different remainders, but the sum of those would be 7. So are there any questions with this problem? I know it's a bit tricky. So yeah, any questions anywhere on this problem? No, it doesn't look like it. Okay, yeah, take some time to think about this one. It is a tricky problem, but there's a lot of good ideas in here that'll help you on some of the homework problems when you're looking at the pigeonhole principle. So definitely, if you didn't quite understand it, definitely try to go back and think a little bit more about this problem. So let's go ahead to the next one. So here we've got a contrapositive problem. And so we're going to prove the following statement by contrapositive. So for all real numbers x and y, if x squared plus y squared is not equal to 0, then x is not equal to 0, or y is not equal to 0. So anybody want to tell me what is the contrapositive for this statement? Yeah, perfect. So we had someone in chat say if x is equal to 0 and y is equal to 0, then x squared plus y squared equals 0. Yeah, perfect. So remember when we have p implies q, the contrapositive is not q implies not p. So the contrapositive is if x equals 0 and y is equal to 0, then x squared plus y squared is equal to 0. So let's go ahead and do this proof then. So we let x and y, let x equals 0, y equals 0. Then x squared plus y squared is 0 squared plus 0 squared, which is 0, which is exactly what we wanted to show. Since the contrapositive is correct, so thus the original statement is true, since the contrapositive is true. So not too bad of a problem, but the thing here is just to remember that sometimes you want to be on the lookout for when you can use the contrapositive. if you had to prove this problem directly, it would have been more complicated than what this contrapositive proof is. You'd have had to show in your proof that x squared and y squared are greater than or equal to 0 for all values of x and y. And then continue with your proof. So you've had to show more steps in order to prove this directly. But with the contrapositive, that made the statement nearly trivial to prove, that 0 squared plus 0 squared is just equal to 0. So in the homework and in the quizzes, we'll give you hints on when you should use contrapositive, induction, et cetera, et cetera. But in your later classes and stuff, this is something to keep in mind, just with proofs in general, that sometimes the contrapositive can be a little bit easier of a path than if you're trying to prove something directly. So any questions on this problem? Awesome. So let's go ahead and go to the next one. So we've got another proof by induction. So here we're going to prove that the sum from I equals 1 to n of 2 to the I minus 1, is equal to 2 to the n plus 1 minus n minus 2. So again, an induction problem, we've got the 4 steps. So first we need to write the problem statement. And so for this statement, we would basically just have this hypothesis here. So P of n just means that the sum from I equals 1 to n of 2 to the I minus 1 is 2 to the n plus 1 minus n minus 2. For n greater than or equal to 1. It's just our problem statement. And then now we have the base case. So here we need to prove that P of 1 is true. Right, so we just plug in n equals 1 to our problem. So we have the sum I equals 1 to 1 of 2 to the I minus 1. And that's just 2 to the 1 minus 1, which equals 1. And then we wanted to show that, hey, this thing is actually just equal to this. And it turns out it is. It's also equal to the 1 plus 1 minus 1 minus 2. Because 2 to the 1 plus 1 would be 4 minus 1 minus 1. So that gives us back to 1. So that's the base case holds. And then the third step for any induction problem is we have the inductive hypothesis. So here, let's just assume that P of n is true. And we'll go ahead for our inductive step and we'll show that P of n implies P of n plus 1. Before we do that, any questions on this first part for this induction problem? Awesome. So let's go ahead and do the inductive step. We want to show that P of n implies P of n plus 1. So we would start then with our n plus 1 expression for I equals 1 to n plus 1 of 2 to the I minus 1. And then if you just want to go ahead and take about a minute or two and finish up the rest of this inductive step here, expanding it out and then getting to the closed form that we want. And just so you recall, we want to show that the sum from I equals 1 to n of 2 to the I minus 1 to the n plus 1 minus n minus 2. Just go ahead and take about a minute to go ahead and work through the rest of this problem. Okay, so hopefully that's enough time. So does somebody want to just explain, just by either unmuting yourself or raising your hand, the trick that we do with summations in order to split the summation up so we can use the inductive hypothesis? Yeah, so just the trick that lets us, so split up the summation. So we have a sum from I equals 1 to n plus something else. How do we usually do that? Which makes implying the inductive hypothesis really easy. So the trick is that we want to kind of think about taking out what the n plus 1th term is from this summation. So what we want is, well, the sum from I equals 1 to n is really the same as the sum from I equals 1, or I plus 1, the same as sum from I equals 1 to n, to I minus 1, and then plus whatever the nth plus 1 term was in this summation, which would have been 2 to the n plus 1 minus 1. And then now, after this step, what we can do is, if we have this by the induction hypothesis, we can replace this with 2 to the n plus 1 minus n minus 2 plus 2 to the n plus 1 minus 1. And this is by the induction hypothesis. And then we can just combine our like terms. So we have to remember that 2 to the n plus 1 plus 2 to the n plus 1, well, that's 2 to the n plus 2. And then minus n minus 3. And so we're really close to the expression that we wanted to show. But we need a minus n plus 1 minus 2. So we just need to rewrite this as minus n plus 1 minus 2, which would give us the same thing. Looks like my main computer is frozen. So hopefully this is all streaming correctly. But I'm not sure. Oh, it is? Oh, good. That's okay. I'm glad because I can't. Yeah, my entire computer is completely frozen, so I can't see or move my mouse even. So hopefully you're able to see this. Okay, that's good that the Zoom meeting is fine then. And yeah, so we just needed to rewrite the expression this way. And then now we can just say as a final concluding statement that by induction, it has been shown P of n holds true for all n greater than or equal to 1. And then that would be the conclusion of our proof here. And then that brings us right to time then. So I recommend looking at some more of these example problems and some of these example proofs. And hopefully that'll help you for some of the later homeworks and then the quiz too that'll be coming up. And if you have any questions, please stop by our office hours or help hours. And hope you all have a good rest of your day. Yes, I do believe that quiz 2 will be on Tuesday, I believe.